All right, welcome back everybody to our last lecture. We're gonna go over our final project, and that'll take us probably 10, 15 minutes, something like that. And then as I mentioned on Wednesday's class, we're just gonna leave the rest of the time for you to read over the project, ask questions on stuff, basically like an office hours afterwards. As far as next week is concerned, the final project is due on Wednesday, which I'll bring up again here in a moment. I'm going to come up with some other office hours times. Usually we have to shift those up in finals week because they don't line up the same way they used to. So keep an eye out for an email later today. I'm going to try to figure out if we can get this room for in-person if possible. But otherwise, you'll certainly be able to do it all on Zoom. So don't feel like you have to make it in person. Either way, we will be able to do it on Zoom. I just got to try and figure out the times for those. So keep an eye out for those emails. Homework 6 is due today, and then the final is the next thing that is up. So let's dig into the final. We'll take a look at it. So the final is posted. If you go into modules on Canvas, it should be right up at the top. There should be the midterm and final project. Obviously, you can ignore all of the midterm stuff. And then if you click on final project, just keep in mind it's to be completed individually. So I put it nice and big and bold and underlined and all that good stuff. If I have any evidence that folks are working together and collaborating on it, unfortunately, that's going to be counted as an academic integrity violation. So please work individually on it. I don't want to deal with that, and really neither do you. It's due at midnight, or a minute before midnight in San Diego time, on next Wednesday, March 16th. You can get the project statement clicking on that PDF. When you're ready to submit your final, it gets submitted just like a homework would, or the midterm. Just come back to this page, and it's a Dropbox, and you can put a zip file in there, and that'll be that. When you get the midterm, it should look like this. There's 3 problems in here, and I tried to draw them from topics that are relevant to the name of the class, which is CENG and Nano 15. So there's one chemi problem, there's one nano problem, and then there's one that's like more of a general engineering, which this time I chose physics, because I don't think any engineer gets through their engineering without having to take some physics classes, so that seemed like a good one. The first one, this physics one, is a simulation, so it's our 4th simulation, something like that. This one's called a 3-body problem. So you may have heard of that in physics. There is no analytic solution to this. You can't sit down and write a formula for the solution of a 3-body problem, but you can simulate it. And so that's what we're going to do here. The formulas we use for updating position look essentially the same as what they did for the midterm. The difference is the acceleration terms, we now have 3 particles instead of 1 particle. And so the acceleration terms will be a little bit more complicated because those are accelerations due to gravity. So they're all interacting with each other all the time, and those formulas are given underneath here. There is, by the way, a good book called The 3-Body Problem. It's a sci-fi book. It's actually a trilogy, ironically, a 3-body problem. So these acceleration terms, these are all going to be due to gravity. We've already seen one of those due to friction. That was in our midterm. But the ones due to gravity are given down here. So there's a few more of them because every particle is interacting with everything else, but that's all of them that I've written here. There's 6 acceleration terms, and so you'll have to code those up inside of your simulation. The way that I'm going to have you run the simulation, if you look at the denominator here, there's these r's in all of the denominators. That's the distance between particles. And when 2 particles get really close, their distance gets really small, and that term generally blows up because the denominator got really small. And so these types of simulations where these kinds of forces, these inverse square law forces, are present, need really small time steps. And so if you look at the size of the time step I'm asking you for, it's pretty tiny. It's 0.001, and I'm asking you to do it 20,000 times. This is going to be an animation, not a plot of the trajectory. And so there's a note on here. I think it's lecture 15 is when we did animations, so you might want to review that stuff. But because the time step is so tiny and there are so many simulation steps, I've added some code down here on the bottom, which will only update your plot every 100th step of your animation. So it does the actual calculation for 99 steps, and then only on the 100th step does it actually update the plot. The way that it's doing that is with this function called mod, which stands for modulus, and it just provides the remainder. So as your index counts up to 20,000, it will check what is the remainder of index divided by 100. If that remainder is 0, then it'll say, oh, okay, go ahead and update the plot. That means you've gone 100 steps or 200 steps or 300 steps. That will make your simulation run a lot faster because MATLAB can do the calculation almost instantaneously. But when we talked about animation, I said the slow part is actually drawing it to the screen. You don't want to draw it to the screen 20,000 times. It's going to take forever. So this little bit of code, if you kind of ignore the if statement and the end statement, this stuff is exactly the same as what it was in lecture 15. So you can always refer to lecture 15. It's doing the same thing. I've just encased it inside of this if statement, so it only happens every 100th step. That's all that if statement is doing, just so that the thing will actually run. If you do it without that, it'll still run, but you'll just kind of sit there and stare at it, and nothing will happen for like a minute or a minute and a half because it's going so slow, because the time step is so small. There is a bonus point, too, which is to make each of the bodies a different color. Which will require a little bit of modification to your code, so you can get a couple extra points to see the bodies in a different color. The I've fixed the axis to -6 and +6 in each of the dimensions for the majority of the simulations as an indicator as to whether you're doing it right or not. The particles should more or less stay in -6 to 6. Once you get up to like steps 19,000 and 20,000, stuff like that, they may have drifted slightly off, and so you can up the range of that axis a little bit if you want. But the majority of the simulation, they should be in the -6 to 6 window. So that can be a little indicator that you're doing things correctly or incorrectly. So that's our first one. It's an animation of one of our simulation studies. Our second one is from Nano Engineering. This is an email that I got about 3 weeks ago. I have modified it a little bit. But a student emailed me and said, I do image analysis, which comes up a lot in nano engineering because we can't see anything with the naked eye. It's very hard to make bulk measurements in nano engineering. And so a lot of what they do is under like electron microscopes, either scanning or transmission or something like that. And so they do a lot of image analysis in nano engineering. And this student said, I'm doing this sort of like brute force in MATLAB. Is there a better way to do it? I was like, of course, and thank you for your final exam problem that you just gave me. So what the student was doing was getting some images that looked like this, the one on the left. His, of course, actually came from a microscope, not from a random number generator, but we'll generate ours randomly. And then what he wanted to do was subdivide them into a quadrant, right? A lower left, a top right, that kind of stuff, and just count the number of particles inside each one of those quadrants. And so that's the first part. These little text box on the grids, I've given you the code to generate those. There's a function in MATLAB called text, and it'll just overlay text on a plot, so there's not much to talk about with that one. So your task on that will be subdivide these into quadrants, count the number of particles in there, and then put the number of particles on top. That's the first part. What the student actually wanted was the ability to set the number of quadrants arbitrarily. So he wanted to be able to say, set 2 rows of quadrants and 5 columns of quadrants, or like what you have here, 4 rows and 3 columns and stuff like that. And so that's the second part is instead of just a 2 by 2 that's fixed, allow the user to set the number of rows and the number of columns for the quadrant divisions that are there, and then count the particles inside of that. And that's what this interface is that I've got up here where I say num(x), num(y). It's how many x quadrants do you want and how many y quadrants do you want. And your code should be able to handle a reasonable number, right? Not 50, because that would subdivide it into extremely small points. But when we go to test your code, we'll just fiddle with the numbers here and see if it works for the majority of combinations. So that's the second one. That one's drawing from nano engineering. And then the last one is chemical engineering. And we've come back to this idea a few times of an equilibrium curve. And we've used alpha everywhere so far. And alpha would give you this blue line that's sitting on here. If alpha is like 2 or 3 or something like that. It is exceedingly rare that a 2-component system can be well approximated by this alpha relationship. So in this problem, you're going to do a similar process of generating an equilibrium curve, but you're going to use a different model, which is called the non-random 2-liquid, actually it's called the associating non-random 2-liquid model, which is pronounced NRTL, or NRTL. It's doing conceptually the same thing. It's saying for a given x, tell me what the y is when these two things are at equilibrium. But if you scroll down a little bit, you need a few more equations to do it. But don't be like terrified by the number of equations on here, right? It's sort of like this last homework where, in order to get the last 2 elements, there were a couple of intermediate ones on here. There's more than a couple here, but just take your time typing through these. It's not like you have to rearrange them or anything like that. They'll all go right in the order, more or less, that I've given here. So just take a few moments to enter them carefully, but you don't have to try to interpret them or rearrange them or anything like that. They're just given in the way that they are. Unfortunately, or maybe fortunately for chemical engineers, because if it was simple, then we wouldn't have jobs. But this is about the simplest extension from this basic alpha model you can get. There are a couple of simpler ones, but they all sort of inflate in complexity pretty quickly. And so your goal will be, on its surface, straightforward. You're going to generate another one of these curves, but of course it'll require a little bit more calculation. There's a bonus problem for this one as well, which is down here. There will be a point where the equilibrium curve should cross the 45-degree line. So unlike that blue alpha curve, which always stays above the 45, this one for NRTL will actually go through it at one point. So it'll look like a bubble and then cross and then kind of curve back on the other side. So if you can use F0 to find that point where it crosses, there are 2 bonus points available for that. The reason I did that is because that is what's called an azeotrope, which makes separation really, really challenging. And so it's useful to be able to identify those before you propose some kind of purification process, because it gets really hard if you have one of those azeotropes in there. Yeah, so those are the 3 problems. There's 2 bonus points on there. And the last thing that I want to do before we sort of wrap it up for now is there is one topic that we went over for a little bit but didn't spend too much time on. I just want to briefly review 2 features of it. There are a couple of places on the project in various parts where Boolean indexing can be very helpful, but just because it's helpful doesn't mean it's required. So I'm going to review this syntax and I'm going to suggest that you try to use it. But if you're struggling with it, it can be done without Boolean indexing. It just looks a little bit different. So I'm just going to review Boolean indexing here for a moment. Let's say we have a vector. I'm going to generate it with just random numbers between 0 and 1. And we'll have 8 elements to that vector. And if we wanted to identify, for example, which of those numbers were greater than a half, greater than 0.5, we can do something like a is greater than 0.5. This returns a Boolean array, or in this case, a vector of Boolean values, logical values. Everywhere that there's a 1, that number is greater than a half. Everywhere that it's 0, it's not. So it's an either or kind of thing. And so, for example, let's say we wanted to count the number of particles that were greater than 0.5, or the number of entries in here that were greater than 0.5. I could say, for example, the sum of a is greater than 0.5, right? And what that does is first it generates the Boolean array, and then it adds up all the numbers in there. So it's adding up all of the 1s in here and saying 5 of those values were greater than 0.5. There's another function that does the same thing. If you happen to Google, you'll see one called NNZ. That says the number of non-zero entries in that vector. It does exactly the same thing in terms of the output. It's like incrementally faster. If you had to do this for like 100,000 or 1 million elements in an array, NNZ is a little bit faster, but sum is fine for everything that we're doing, so you can use either one. Either one will count the number of 1s inside of a logical array. The other thing that you can do with Boolean indexing, so that's sort of tip 1. Tip 2 is you can use that to overwrite those particular values. So for example, if I wanted to say take all of the values that are greater than a half and replace them with like 999 or something like that, or whatever the number is, I can say take all of a, which is greater than 0.5, and assign to it the value of 999. And so the way to interpret this is the first thing it does is it figures out 999, but the second thing it does is where does this go? Well, it generates this Boolean index, or this Boolean array, and says, okay, take all of those values in A for which A is greater than 0.5 and replace them with the number 999. All of which we did in our Boolean array discussion. It's just we didn't cover it a lot. So I thought it was worth reviewing here. And I will only caveat that again with the point that if you don't like this, if you don't want to use this, you don't have to. I didn't set up any of the problems that require this, but it can be a very convenient method for a couple of the different things that you have to do in the midterm or in the final, which is why I reviewed it here. And this will get posted too. This is part of our, I mean, not this, I just did this in the command window, but this Twitch broadcast that we're doing right now will be posted so you can review this later while you're working on things. So that's that. I am going to pretty much mute myself for the remainder of the class. I am over on Canvas chat. If you have any questions or clarifications for the final, you're welcome to throw them up over there. But otherwise, I will just hang out for the remaining 30 or so minutes. If I don't talk to you again, thanks for hanging out with us on CENG 15 and Nano 15. I hope to eventually see you in person for everybody that's on Twitch. We are coming back in person for the spring, so that'll be great. I'm looking forward to it. I hope you come say hi. I hope we have another class together. Good luck on the final. Good luck on your other finals. And I will see you when I see you. Bye, Twitch. I'm still here, Twitch. I'm just muting my mic, and we're just going to hang out for the rest of the 30 minutes. So that was actually really good. It was an in-person question. I forgot to unmute myself for Twitch. The question was, do we have to show up for the final to like turn in the code or talk about the code? No, just submit it, and that's all you need. Though there are times on the schedule of courses that list like you have this 3-hour period for your final. You can completely ignore those. They have no meaning at all for this class. For this class. Do what you need to do for your other classes. I don't know what they do. this up. Okay, everybody, it is 3:50, so I'm going to wrap up the Twitch stream now. This will get posted in probably like an hour or something like that. And that concludes our entire class for Twitch. So we'll see you maybe in the office hours next time, Twitch, but otherwise, good luck on your other finals. We'll see you soon.